Okay, welcome to watch this video. Now we are going to introduce our project, multi-classification task of COVID-19 long CT images based on ResNet. Our group members are Chen Yijun, Zhu Yonghao, Wu Yuhan, Zhu Di, and Xu Zizhao. Okay, let's start with the first part, abstract. The outbreak of novel coronavirus pneumonia around the world has seriously affected people's normal work and life. Therefore, in the current pandemic, testing for COVID-19 is particularly important. RT-PCR is a good testing method, but because of its efficiency and accuracy problems, it does not fully meet the medical needs. Hospitals and doctors need more means to detect and screen the novel coronavirus. In virus screening, using deep learning to identify and classify long CT images is a good choice. In order to get higher classification accuracy, this study builds a model based on ResNet to detect long CT images from around the world. Unlike most previous studies, this study divided patients' long images into 3 categories to help doctors make better, faster diagnosis. This study builds the normal on the TensorFlow framework and finally achieved the best classification accuracy of approximately 87.2% after adjusting the batch size and epoch numbers. The experimental results demonstrated the effectiveness of the proposed model. Okay, let's come to the next part, introduction. The novel coronavirus pneumonia, namely COVID-19, has spread rapidly around the world since it was first discovered in Wuhan in 2019 and has been a serious threat to people's health. Due to the seriousness of the epidemic, there have been many social problems such as casualties and economic losses around the world. Therefore, the prevention and control of the epidemic has always been a hot topic of discussion and research. In the prevention and control of the epidemic, real-time detection of the novel coronavirus plays a vital role. Typical symptoms of COVID-19 include cough, difficulty breathing, and loss of smell, but it is not possible to fully define whether a patient is really infected with COVID-19 simply by the symptoms that they experience. In the detection of viruses, nucleic acid testing is a very effective means. In nucleic acid detection, RT-PCR technology is widely used in the detection of novel coronavirus because of its high sensitivity and fast detection speed. However, there is always a risk of false negative or false positive in real-time RT-PCR detection. RT-PCR detection alone cannot obtain the most accurate detection results. As a result, many doctors and researchers began to use CT to detect novel coronavirus diseases, and in some cases, CT tests yielded better results. Although there are still many challenges in the detection of novel coronavirus by CT, it is undeniable that chest CT has become one of the mainstream detection methods with its low-cost, effective, and accurate characteristics. Although the sensitivity of CT detection is high, the analysis and interpretation of CT requires professional medical imaging doctors. However, in the context of this epidemic, medical resources are very scarce, and professional and experienced medical imaging doctors are no exception. Therefore, artificial intelligence automatic detection of CT images has begun to be applied to different medical scenarios to relieve the diagnostic pressure of radiologists. At present, researchers have proposed automatic identification of CT images to detect whether patients are infected with novel coronary AI. However, with the further development of epidemic, only by analyzing CT images to know whether the patient is negative or positive for COVID-19 cannot fully meet the current medical needs. In more scenarios, doctors need more precise classification to get a more detailed understanding of the patient's condition in order to develop a follow-up treatment plan. In this study, deep learning is used to classify long CT images into three types: normal, novel coronavirus pneumonia positive, and long opacity, which is non-COVID long infection. This study built model based on ResNet 50 using the framework TensorFlow and test the results under different batch size and epoch, which will be described in details below.
Okay, hello, my name is Wilhelm, and now it's my turn to introduce the ResNet. So as my team member taught in the previous, our project involves CT image recognition of COVID-19 patients. So it is very important to select efficient neural network. How to choose? For some problems, is it necessarily beneficial for us to depend the layers of the neural network? The answer is necessary. Therefore, how the new layer can improve the performance of the neural network deserves our careful consideration. For example, as shown in the figure left. So I suppose that the F star is the optimal value. F1, F2, F3, 4, 5, 6 is the different models, and F1 is the simplest model. The size represents the complexity of the model. We can find the closest model to the optimal value in F1 regions is this point, and F2 region is this point. Find this point, and here. Now and then we can compare the distance, the best model in different regions, to the F star best optimal value. We can find that although the model in 5-6 region is more complex, it is farther apart than that in F3. here. Yeah, this is because when some model training, it will occur as the complexity of the model increase. And then, as we can see in the right, how can you improve the model before this idea? Maybe we can use the subject relation, which means that the layer more complexity model is trained strictly within the scope of the previous model. In this way, when the complexity of the later model can be ensured, and the distance from the f star will not be longer. In other words, each additional layer should more easily contain the region functions as one of its elements, which is the basic, which means it is the classical ResNet idea. And then let's talk about reduce block. Let's say that our new functions. Suppose our new functions fs. Suppose we have functions fx equals to x plus gx. In one simplest case, when gx function doesn't do anything, then we will have our region functions fx. If gx does anything operation, then the original model fx will be bigger than the previous. As shown on the left, we can see that it has the convolution layer, activation function, and the convolution layers. Active functions. We need to go through the following convolution layer to reach the top layer. The idea of a reduce block is that when the function inside the dotted line doesn't work, we still have to go to the top layer. We can just by adding a new path, which means that the complexity model contains the simplest models. Yeah, and then let's look at the intent design of the ResNet reduce block. So as we can see, here are two implementations. So the left. Here are two implementations. So the left. When we input the value x through 3x3 convolution layer pooling, activation layer, 3x3 convolution layer, repooling, and finally output. A path is added in the direction of the input x, so that it can be intended directly. Or we add another 1x1 convolution layer to the new path to change the channel. For example, if the convolution layer inside the dotted line is going to change our channel, then the convolution layer of 1x1 is going to change our channel into the proper range, and then add back the original values. By the way, of course, radius have a different design. In fact, our new path can be at anywhere in the front of the pooling, behind it, and pooling. Also, the pooling can also be placed in the bottom. Anyway, we should try the different design. Yeah. So next, If you look at the architecture of a ResNet, the most important features of ResNet is the additional operation. Here are two type of ResNet blocks. The first is have the height and width with a amplitude of 2, usually doubling the channel. The first step is to two-step ResNet block, from which a bunch of ResNet block with the same height and width as structured upward. Its architecture is similarity to VGG and Google Net. After a 7x7 convolution layer with 64 output channels and 2 steps, it is followed by a 3x3 maximum convergence layer with 2 steps. The difference is that ResNet should add a batch normalization layer after each convolution layer. And so, although the main architecture of ResNet is similar to Google Net, ResNet architecture is simpler and easier to modify. These factors all contributed to the rapid and widespread use of ResNet. And then we should describe the reduced block codes. Google Net follows with 4 modules composed of inception block. ResNet used 4 modules composed of radius. Each of these use several radius with the same number of output channels. The number of channels in the first module is the same as the number of input channels. Since the maximum convergence layer with a step of 2 was already used, there was no need to reduce the height and the width. Each subsequent models doubles the number of channels and has the height and the width of the previous module in the first radius block. And now let's implement this module. Should notice that we made special use of the first module, then add all radius to ResNet. Well, each module used 2 radius block. Finally, just like Google Net, a global mean aggregation layer is added to ResNet, as well as a full connection layer output. Each module has 4 convolution layers, excluding the convolution layer of identity mapping, with the first convolution layer and the last fully connected layer. There are 18 layers for this reason. This model is often referred to as ResNet 18. Different ResNet models can be obtained by configuration different number of channels and the reduced block in a module, such as the deep ResNet 152 layers. And then it's all my part to introduce the ResNet. Now it's my turn. Now it's turn to my teamwork. Yes, thanks.
Okay, so I'm going to introduce you the dataset of our project. And the dataset used in this paper is from the COVID-19 radiography database on Kaggle. Kaggle is an online platform for developers and data scientists to run data science competitions, host databases, and write and share code. We can find many sets on Kaggle. So we can find Kaggle's website by opening our browser and searching for Kaggle directly. We can just input Kaggle here. And the first one is the official website of Kaggle, and we can click it. So here, our dataset is from COVID-19 radiography database. So we can directly search for COVID-19 radiography database, and then we can see this dataset. COVID-19 radiography database. And this one is what we need. After we click it, we can see there are lots of folders in the dataset, and what we need is the 3 folders. The COVID folder represents lung CT images of patients with COVID-19. The normal folder represents lung CT images of normal individuals, and lung opacity folder represents lung CT images of patients with other types of pneumonia besides COVID-19. We can click on the folder to see what's inside. The image folder is our objective, and we can see there are 3,616 files in the folder, and similarly there are after we click the lung opacity, we can see there are 6,012 non-infected COVID-19 lung opacity CT images. And after we click the normal folder, we can see there are 10,192 normal CT images, and this database is still being updated. Before the experiment, the image data is pre-processed. The dataset is divided into training set and test set into 9:1 ratio. After the division, there were 3,254, 5,410, 917 COVID opacity and normal images in the training set, and 362, 602, 1,020 in the test set. Well, the next step, I'm going to introduce you the code part of our project. The first step is to import the libraries we need, such as some basic libraries, pandas, numpy, cv2, and so on. Then we put the path of the dataset we just obtained and the test set into different parameters. Because we have 3 different types of CT images, so we use 3 different parameters to store their paths here, and for both train and test we do the same thing. In the next cell, we create 2 kinds of arrays to store images here. Now we need a method to read our dataset. We define a method called readImage to get the images. The input of the method are the array of the image and the path of the dataset, these 2 parameters. Next, we will read the images one by one from the dataset directory and store them in the array we just input. But there is a problem here. Well, the original image size is 299 by 299 pixels, but due to the memory limitation of our machine, we can't read such a large image smoothly, so here we change the size to 56 by 56 pixels to make sure it works correctly. Then we change the Python array to a NumPy array to continue our task. From our dataset, we can know exactly the number of images corresponding to each category, and then we classify them by marking COVID as 0, normal as 1, and lambda opacity as 2, respectively. Then we normalize all the images here. Here we use 1 hot to process all the labels to ensure that the task goes smoothly. 1 hot encoding, also known as 1 valid encoding, mainly uses n-bit status registers to encode n status, each with its own independent register bits and only 1 valid at any given time. 1 hot encoding is the representation of categorical variables as binary vectors. This first requires mapping categorical values to integer values. Each integer value is then represented as a binary vector, which is 0 valued except for the index of the integer, which is marked as 1. Here is the base model, this line, and we use the ResNet 50 that comes with Keras to build our base model. Here, the parameter we use to initialize is ImageNet. Well, actually, ImageNet is an image database organized according to the WordNet hierarchy, in which each node of the hierarchy is depicted by hundreds and thousands of images. The project has been instrumental in advancing computer vision and deep learning research. It is an already trained parameter. Using the parameter for initialization, we can speed up the training process easily. And the parameter of the include top, here, this one, should be false, because we need to define the outer layer by ourselves. Then we use the 3 lines here to define the rest of the network. The checkpoint is used to save the best model, this one, and after that we just need to compile the model, and finally in the last step we can start our training here, and that's the basic component of the code part.
Now, let me introduce the loss function used in the experiment, cross-entropy loss function. Cross-entropy is a concept in information theory. To understand cross-entropy, we first need to understand some related information theory bases. The basic idea of the amount of information is that an unlikely event actually occurs, and we received more information than a very likely event. Using an example to understand, suppose we received the following 2 messages. A is the sun rose this morning. B is there was a solar eclipse this morning. We believe that the amount of information of message A is so little that it is not necessary to send, while the amount of information of message B is very rich. Using this example, we will define the basic idea of the amount of information. Events very likely to occur has small amount of information. In extreme cases, events that are bound to happen should not have the amount of information. 2. The unlikely event should have higher amount of information. The amount of information contained in the event should be negatively correlated with the probability of its occurrence. Assume that x is a discrete random variable. Its value set is x1, x2 to xn, and the amount of information of the event x equal to xi is defined as this, where log represents the natural logarithm and the base is e. In the formula is the probability of variable value, which should fall between 0 and 1. Draw the value of the above function when p is equal to 0 to 1, as shown below. When the probability value tends to 0, the amount of information tends to be positive infinite. When the probability value tends to 1, the amount of information tends to 0. This function can meet the basic idea of the amount of information and can be used to describe the amount of information. The amount of information formula given above can only deal with the amount of information when random variable takes the specific value. We can use entropy to describe the average amount of information of the whole probability distribution. The specific method is to find the expectation of the above information function about probability distribution P, and the expected value, that is, entropy, is this. Suppose that the true probability distribution of the random variable x is Px, and we use an approximate distribution Qx to model when dealing with practical problems. Because we use Qx instead of real Px, we need some additional information to offset the impact of different distributions when we specify the value of x. The average amount of additional information we need can be calculated using relative entropy, or KL divergence, which can be used to measure the difference between the two distributions. In fact, the cross entropy is closely related to the KL divergence just introduced. Let's change the above KL divergence formula. The cross entropy x HPQ is equal to, if P is regarded as the true distribution of random variables, and HPX of the left half of KL divergence is actually a fixed value. The change of KL divergence is actually determined by the cross entropy of the right half. Because the right half contains an approximate distribution Q, we can regard it as the real-time output of the network of our model, and regard KL divergence or cross entropy as the difference between the real label and the network prediction result. So the purpose of neural network is to make the approximate distribution Q approach the real distribution P through training. The effect of optimizing KL divergence should be the same as that of optimizing cross entropy. The reason why we choose to optimize cross entropy instead of KL divergence in deep learning may be to reduce some computation. After all, cross entropy is less than KL divergence. In the multi-label classification task, that is, a sample can have multiple labels. For example, if a picture contains cat and dog at the same time, the picture will have two labels belonging to cat and dog at the same time. In this case, we take the sigmoid function as the output of the last layer of the network, and regard each neuron of the last layer of the network as a category in the task. Taking the image recognition task as an example, the output of the last layer of the network should be understood as the probability that the network thinks that the image contains this category of objects. However, there are only two possible values for each type of real label, namely, the picture contains this type of object, and the picture does not contain this type of object, which is a binomial distribution. To sum up, if each category of multi-label tasks is analyzed separately, the true distribution P is a binomial distribution and the possible value is 0 or 1, while the distribution Q of network prediction can be understood as the probability that the label is 1. In addition, because each class is independent in the multi-label classification task. The sum of the probability values output by the neurons at the last layer of the network is not equal to 1. For one class of multi-label classification task, the cross-entropy loss function is this.
Hello everyone, my name is Junhao Zhu. Next, I will present to you the experimental result and conclusion of our project. Firstly, the experimental result. For the purpose of this study, different results of the ResNet model were tested at epoch equal to 20 and epoch equal to 30. And then bench size equal to 32 and bench size equal to 64. Respectively, as the table shows, we can find the experiment that its performance better on the test side when the epoch and bench size are larger. The highest accuracy on the test side reached 87.2. Also, the best performing models on the validation side was recorded during the training period, with an accuracy of up 100% on the validation. However, the accuracy of this model in the test site was below 18%, indicating that the performance on the validation side can only be used to indicate a trend and is not representative of the final result. To further elect the effectiveness of ResNet for the multi-classification task of Covid-19 long CT images, we choose a neural network widely used in the field of computer vision, which names Model Net V2. Under the same experimental conditions, the accuracy of Model Net V2 was 65.98%, as shown in the figure. It can be seen that the results of ResNet are significantly better than those of Model Net V2. Thus, we further demonstrate that ResNet performs well in the multi-classification task of Covid-19 long CT images. And unlike previous Covid-19 classification tasks, the main aim of this study was to classify the long images of Covid-19 patients in more detail than just discussing whether or not they were infected with Covid-19. The main question was how to accurately determine when a patient was suspected of being infected with Covid-19 and when the patient's lungs had shortness that resemble infected Covid-19. This is more detailed and accurate classification, so a deeper neural network is considered in this study. To avoid degradation of deep neural network, the study considered building a model on the top of ResNet models with good results. And next is a concluding section. And the outbreak novel can reverse COVID-19 around the world has seriously affected people's normal work. People can only work at home or suffer from the ill, and lots of people even lose their life. So the detection of COVID-19 is therefore particularly important in the COVID pandemic. And the normal test with PT-PCR test, right, it's a good detect method, but it does not fully meet medical need due to its efficiently and accurate illness. Hospitals and physicians need additional tools to detect and scanner for the novel coronavirus in various scanning. The use of deep learning to identification and classic CT images of lungs is a good option. To obtain higher classification accuracy, this paper built a ResNet-based model to detect lung CT images from around the world. Classification avoid COVID-19 lung CT images into three types, namely COVID-19 positive, non-infectious COVID-19 lung optis, and normal lung. The aim to the aim of this paper is to show that using deep learning, we can indefinitely CT images can help hospital and doctors to do the most long scanning of patients' CT images and reduce medical burden on medical images doctors during an outbreak. As deep learning techniques continue to advance excellent algorithms and models emerge, deep learning will become increasingly good at the task of CT detection and classification. And in the future work, we also need to expand the amount of data. That's because considering the experimental results, we found that would still be better as the amount of data becomes larger. And also to promote our funding is right, we also need to try to compare with more neural networks, such as the classical neural network like VGG16, that we can compare with the results between other neural network and find which neural network can performance better. Maybe use that neural network, we can do more things in the during COVID-19. In addition, with the emergency of highly transmissible strains and large scanner efficiency, just like now, the Omicron led more than 18% Chinese got COVID-19. There is a need not only to determine whether the patient is ill or not, but also to understand the whole lung situation. And we will also try to apply the neural network to detection and the treatment of the sequelae of the COVID-19, and then gradually develop it to be able to treat a wide range of lung disease from CT images of lungs. That's all of project. Thank you for your listening.